So polynomials, they can be added, subtracted, multiplied, and they can even be divided. Polynomial division is a bit more abstract though. If I asked you 12 divided by 4 and you said 3, you're thinking that cutting 12 4 ways leaves 3 in each chunk, and you're right. That doesn't have the same meaning though when I ask for 10x squared plus 27x plus 18 divided by 5x plus 6. I'm betting you're not thinking that 10x squared plus 27x plus 18 cut 5x plus 6 ways leaves 2x plus 3 in each chunk. Of course, you're probably also asking, why would anyone care? At this point, you may just have to trust me that there are good and valuable uses to dividing polynomials, like confirming roots, but that's later. For now, I'm just going to show you how to divide polynomials. Later, I'm going to show you a shortcut, but since that shortcut doesn't always work, we're going to save it for another time. It may help to think about division a slightly different way. 12 divided by 4 is 3. So what that means is, if you had 4, and you needed to multiply it by something to get 12, that something would be 3. This works the same way for polynomial division, because if you had 5x plus 6, and you needed to multiply it by something to get 10x squared plus 27x plus 18, that something would be 2x plus 3. Now, how do we find that something? Well, there are two good ways to do it: polynomial long division and synthetic division. Polynomial long division always works, but it is intensive. Synthetic division is much faster, but it only works in limited cases. So for this video, I'm going to limit it to long division. I'll show you synthetic division in a later video. Now, the thing about polynomial long division is it really only makes sense if you grok regular numerical long division. So if you don't remember regular numerical long division, stop this video now and go check out my other video on the subject of regular long division. So polynomial long division works a whole heck of a lot like regular long division. We're going to take all of the values and terms of the dividend. We're going to divide them by the divisor, and we're going to wind up with a quotient. The quotient, or answer that we wind up with, if it were multiplied against the divisor, would get you back to the dividend. But although this problem is accurate, it's not written in the best format for us to use. It would be much better written as a long division problem. So the first thing you do is you rewrite your problem as a long division problem, with the dividend underneath the long division bar, the divisor sitting outside, and the quotient is going to wind up on top. I've put a long division problem on the right here to point out an important consideration when you're doing long division. If I was dividing 1065 by 8, notice the 0 is missing. I have to have a 0 there for us to know that this is 1065. In a polynomial division problem, it is possible to be missing a term. For example, if this 43x wasn't here, then this would just say 12x squared plus 35. But we'd be missing the x term, and it would be important for you to have it and see it for the purpose of being able to do the problem. If there wasn't an x term, we'd need to put a 0x term there, just like we leave a 0 here to make sure we know where everything goes. So let's make it happen. In regular long division, we take the entire divisor and see how far we can comfortably divide it into the dividend. So we'd see how many times 4x plus 5 goes into 12x squared. Well, that's a little too complicated. So we're going to simplify it by just saying how far can the 4x go into the 12x squared. More specifically, what times 4x would get us to 12x squared? Well, to make the 4 turn into 12, we would need a 3. And to make the x turn into x squared, we would need an x. So 4x goes into 12x squared 3x times. Or 3x times 4x makes 12x squared. So 3x is going to be the first term of our quotient. The next step in long division is to take that first element, that first part, that largest value, that first term, and multiply it down against the divisor for the purpose of creating an amount that will then take away from the dividend. The whole point of division is to remove from the dividend everything that can be divided out. So we're going to multiply 3x times 4x plus 5 and put it down here. 3x times 4x makes 12x squared. Of course it does. That's what we needed so that we could get this to go away. But we're not done, because it would be incomplete for us just to multiply the 3x times the 4x and be done. There's still a plus 5 here. So we're going to have to take the 3x times the 4x and get 12x squared, but we'll also have to take the 3x times the 5 and get 15x, which appropriately goes here. Notice that when I multiplied down from my quotient to my divisor, I created an x squared term and I put it in the x squared column. I created an x term and I put it in the x column. I don't have anything for the constant column yet. I'll get there in a minute. My next step in long division, since my whole purpose is to get things to leave the dividend, to divide out of the dividend, is to take these new multiplied down terms and remove them from the dividend. It's important you recognize that what we're doing now is removing what we've identified as divide outable from the dividend. And since we're removing, we're taking away. Here's what I do to remember that. When I draw the long subtraction bar, I go ahead and change the signs of each of these terms. If it was positive, I turn it negative. If it was negative, I turn it positive, because I'm taking away. Now, the 12x squared minus 12x squared, of course, leaves us with nothing. That was the whole purpose, to get that entire term to go away. We're not going to be so lucky with the next term. 43x minus 15x leaves us with 28x. Understand that 28x is what remains from the original dividend that wanted to be divided out, but didn't get divided out by the first term. It will have to get removed by the next term. In regular long division, your elementary school teacher taught you that now that we're going to need the next term, the next item, the next line, go ahead and bring it down so that we're ready to use it. We ignored it before because we weren't ready for it. Now we are. So 28x plus 35 is what remains from the dividend that wants to be divided by 4x plus 5. So our next job is to say, fine then, what times 4x would get me to 28x so I can remove it. 28x divided by 4x is what? Or what times 4x would give me 28x? I believe that value would be 7. So 3x plus 7 is our quotient, but is it complete? Does it take care of everything? We're going to take that 7, multiply it down into the 4x plus 5, and see if it gives us enough to get rid of all of this. 7 times 4x is 28x, and 7 times 5 is 35. This is looking like a pretty good match. Remember, our purpose here is to take away what remains from the dividend. So I'm going to change the signs of both of these terms before I draw my big subtraction bar. And then 28x minus 28x leaves me with nothing, and 35 minus 35 leaves me with nothing. I have no remainder. And I also have an answer, 3x plus 7. 3x plus 7 is the value that if I were to multiply it times 4x plus 5, I would wind up with 12x squared plus 43x plus 35. See if you can do a quick FOIL of those two and prove that it's true. There is a lot of stuff going on in these problems, which is why I want to show you another example. 8x cubed plus 2x plus 33 divided by 4x plus 6. And there's a problem right off the bat. It's this problem I mentioned earlier. If I was taking 8 and dividing it into 1046, I couldn't just leave the 0 off and make it look like 146. That would be lying about the value of the 1. Well, in polynomials, we are in fact allowed to just leave the term out. There's an 8x cubed term. There is no x squared term. There's an x term and there's a constant term. But that missing x squared term is akin to leaving off this 0 in this division problem. We can't leave it off when we go to do the long division. It needs to be there. So when I write my long division problem, I am going to make my big division bar like I do for long division problems. But here where the x squared term goes, I'm going to put a 0x squared, respecting the fact that everything has its place. And now I have a column for every kind of term. And finally, before I get started, I'm going to warn you, this one's not going to work out evenly. That's okay. Sometimes they don't. You have a remainder. Here we go. I'm going to do this one a little faster, but I'm still going to talk you through it. 4x plus 6 goes into this some number of times. We'll start by only looking at the 4x and asking how many times does 4x go into 8x cubed? 4x times what makes 8x cubed? Well, 4 times 2 is what you need to make 8. And something times x makes x cubed, there must be an x squared. 2x squared is the first term of our quotient. So we're going to take that quotient, that first term, and multiply it down into the 4x. But we will also multiply it into the 6 at the same time. 2x squared times 4x makes 8x cubed. Of course it does. We chose that on purpose. But the 2x squared also has to multiply times the 6. 2x squared times 6 will make 12x squared. And that's going to go in the x squared column that we created on purpose because we knew we would be needing it eventually. Next step, remove the 8x cubed and the 12x squared from the dividend because we divided them out. To remove them, you subtract them. Change their signs before you draw the big subtraction bar. And then see what leaves. The 8x cubed is taken away by an 8x cubed. Nothing there. The 0x squared has a 12x squared being removed from it, and therefore we're going to wind up with negative 12x squared. Now we ignored the 2x and the 33 earlier because we knew we wouldn't need them yet. We are going to need the 2x in the next term, so I'm going to go ahead and bring it down so it's ready for me. I could also bring down the 33, but I'm not going to need it yet. So negative 12x squared plus 2x and the 33 we're ignoring for the moment are what remains from the dividend that wants to be divided by the divisor. What times 4x would get me to that negative 12x squared, and the rest would come along for the ride? Well, to turn 4 into negative 12, I would need negative 3. To turn x into x squared, I would need x. So negative 3x times 4x is what makes negative 12x squared. But we're not done because we have to take that negative 3x times the 4x, but also times the 6. So negative 3 times 4x makes negative 12x squared. That's what we chose on purpose. But negative 3x times 6 makes negative 18x, and that goes here. Next, and apologies for the crowding, we're going to take that negative 12x squared minus 18x that we multiplied down off of the divisor and remove it from the original dividend. That means we're going to take this negative 12x squared and we're going to change it to a positive 12x squared. We're going to take this negative 18x and change it to a positive 18x. That's how we take away, and we do that before we draw the big subtraction bar. And now we combine. Negative 12x squared and positive 12x squared disappears. That's what we wanted. 2x and now positive 18x makes a total of 20x remaining from the original dividend that wants to be divided. And the only other thing remaining from the original dividend that wants to be divided, we've divided everything else out, is the 33. We're ready to bring that down now and see what we can do with it. The 20x plus 33 is the only thing left that hasn't been divided away by the quotient that we've created. What we need now is our final term in the quotient, which, when it multiplies against the divisor, will get this remainder from the dividend to disappear. And like each time before, we're going to take a term times the 4x and try to get the 20x to go away. Something times 4x makes 20x. That one's pretty simple. I think it's 5. So now we'll take that final term in the quotient, multiply it against the whole divisor, and try to take it away from what remains of the dividend. 5 times 4x makes 20x, and 5 times 6 makes 30. You may notice this doesn't wrap up with a nice little bow like it did the last time. So now we'll go ahead and take care of removing from the dividend the last that we've divided out. The 20x is being removed, the 30 is being removed. And now we can draw our big subtraction bar. 20x minus 20x leaves me with nothing. 33 minus 30 leaves me with 3. Now there is no term I could put up here that I could multiply against the 4x to make 3, and there's nothing else to bring down. That 3 is what remains from the original dividend that wants to be divided but can't be. Because it remains, it's what we call a remainder, which in some cases could be written as a remainder. I'd like to be a little bit more precise. That 3 that remains from the dividend wanted to be divided by the divisor. It still does. And so what it's going to wind up being is the 3 that is being divided by 4x plus 6. We just can't do it cleanly, so we leave the instruction for the next guy. And this is our answer. It's the quotient, the result of our division, and the answer to the question, if 4x plus 6 times something would get me to 8x cubed plus 2x plus 33, that something would be 2x squared minus 3x plus 5 with a remainder of 3 over 4x plus 6. That was a lot of stuff. The secret to polynomial long division is that it is exactly like regular long division. You take a big term you want to divide apart and you divide it by a smaller term. Everything has to be in its place. You figure out how far you can divide in and then you remove, and then you do it again until you get it all. Caution, the very most common mistake you're going to make in polynomial long division is a sign error. Watch the signs carefully, and when you remove at each removing step, you are subtracting. So positives turn to negatives, negatives turn to positives. You're taking away. If you get stuck somewhere, back up a step and try to remember what it is you're trying to accomplish. Not what's the next step. What are you trying to do? So, polynomial long division sometimes works out nice and easy, sometimes requires a little reformatting and doesn't work out particularly nicely, takes a lot of time and effort, and there's a shortcut that goes much, much faster but doesn't always work. This is a concept that you can't just see and then you know. You've got to try it out. Go find some samples and work them out. Good luck, and I hope you've gotten smarter.